So do you guys have any questions about anything? It's all good. All right, well, in that case, I will just dive into the additional examples that we haven't quite got to yet. I'll start with something I mentioned, which is kind of a little bit tricky, which is the integral of like a fourth power of, say, we can do sine or cosine. I'll do sine to the fourth. This one's kind of a pain, but we can do it. So sine to the fourth theta, well, we saw last time that the integrals of like odd powers, by last time I mean last Wednesday, of course, but you know, the integrals of odd powers of sine or cosine, not too bad, right? But even powers, a little bit trickier. So the way you do this is to look at this as sine squared theta squared, right? But the thing is, we have an identity for sine squared, right? What's the integral for sine squared? What's the identity? It is 1/2 of 1 minus the cosine of 2 theta, right? So you got to take all of that, and you got to square it. What happens when we square that? Well, we get a fourth, right, up front. And then that gives us, when we multiply out this 1 minus cosine 2 theta squared, what do you get? You get 1 minus 2 cosine 2 theta, right, plus cosine squared 2 theta. Right? Now, the first two terms, like the first term is like totally easy, right? That's the integral of 1 with respect to theta is just theta. And this one, I can make a u equals 2 theta substitution, then du is 2 d theta, or if you like, d theta is 1/2 du, right? So with that substitution, I get, you know, let's see here, 1/4. So the 1 integrates to theta, so I've got 1/4 theta, you know, let me just say 1/4 theta. Let's see here, so that's what, minus, what's 2/4? 1/2 minus 1/2, the integral of cosine 2 theta, which is cosine of u, du of d theta, which in this case is du over 2. So this 1/2 I'm getting from the minus, let me write that as 2/4 just to be kind of more keeping track of where things are coming from. So that's the 4 that was there before and the 2 that's there. And of course what happens is you get a net of 1/4 there. We've still got the integral of cosine squared 2 theta d theta, which I haven't dealt with yet, right? Although maybe I should just go ahead and change that to u. I mean, it's up to you guys. What do you guys want to do? Should we use that u substitution, this u substitution on this piece as well? If we did, what would that look like? Instead of having 2 theta, we could put a u here, right? And d theta would be what? It would be du over 2. So what's the integral of cosine? It is sine, right? So these 2's cancel. We get theta over 4 minus 1/4 sine of u plus 1/8 integral of cosine squared u du, right? Now, can you guys tell me what's the identity for how do we integrate cosine squared, or what did we use there? So at the start of this problem, I used the half angle formula for sine, right? I used that sine squared theta was equal to 1/2 of 1 minus cosine 2 theta, right? So now we need to use the similar identity for cosine squared, which is what? It is let's see here, sine of u. So I'm going to get plus 1/16 the integral of 1 plus the cosine of 2u du. Now, the integral of 1 with respect to u is just u, right? So I get a u over 16 from this 1 here. Let's see here, plus u over 16. And then what's the integral of cosine 2u? Tell you what, I'm running out of chalk. Yeah? The sine, but almost. But let me do it over here. The integral of cosine of 2u du. So we're going to let 2u w equal to 2u. And with that, this is equal to the integral of cosine of w times dw over 2. See, because this says that dw is 2 du, which says that du is 1/2 dw. So if I swap out this du, I get 1/2. The point is, because we got a 2 there, we're going to have to divide by 2 in the antiderivative. So you're almost right. It is a sine of w, but we got to divide by 2. You know. So with that little sidebar, the integral of, cosine 2u, which I just did over here, is, well, you notice I've got a 16th out here. I got to keep track of that, right? So I've got 1/16 times 1/2, which is 1/32. Sine of 2u plus a constant, right? But what was u equal to? Yeah, what was u? Remember u? U was equal to 2 theta up here, right? So I got to undo that. This gives me, well, let's see here. What's 1/4 plus 1/16? Oh, I should, hold on a second here. We got theta over 4 minus 1/4 sine of 2 theta plus 2 theta over 16, right? Plus 1/32 sine of 2 times, what's 2u? 2u is 2 times 2, it's 4 theta, right? And notice that we can collect these two terms together, right? So I'll do that before I write my final answer. What is 1/4 plus 1/8? 3/8, right? So we get 3/8 theta minus 1/4 sine of 2 theta plus 1/32 sine of 4 theta plus a constant. And that is why last Wednesday I told you that integrals of even powers of sine or cosine are a pain. Because this. It's nothing that you can't do, it's just more, It's this half-angle identity done not once, but twice. You have to do it twice because after you do the first application of it, you end up with an integral of cosine squared still. You got to take care of that, and so you need yet another application of cosine squared. But as horrible as it is to even talk about this, if I was to ask you to integrate the 6th power of sine, you should kind of see how to do it, right? If we were to integrate the 6th power of sine, I mean, I'll start it. I'm not going to finish this, don't worry. So this would be the integral of sine squared cubed, right? And so that's like 1/8 integral of 1 minus the cosine of 2 theta cubed. And then that, well, we know how to cube things, right? That's 1 minus 3 cosine 2 theta plus 3 cosine squared 2 theta. Minus cosine cubed 2 theta. So actually it's a little bit different when you get into the details here, but the point is we already know how to integrate a cubed cosine, and we already know how to integrate cosine squared, so we can do it. Don't worry, I will not ask you to do this integral. I have no interest in grading this problem either. My point to you is just that we could do it if we wanted to, okay? That's all. Right. What about integral of like cosine to the 4th? What would the difference between this and the integral of cosine to the 4th be? With cosine, you have cosine squared squared, right? So the only difference really is that it puts a plus here instead of a minus in the in the formula for the cosine squared theta is 1/2 of 1 plus cosine 2 theta. So this identity comes into play, and that would change that to a plus, but it's pretty much the same song and dance. It's just this minus changes to a plus, which makes this a plus, which makes that a plus, and that a plus, and that a plus, and that a plus, and it's very, very similar, actually. Right. So, all right, so let's go back to last time. So, more often than not, as I'm teaching calculus, I find it usually suffices just to see if students can integrate just even the square of sine or cosine. Like, that's the first thing in terms of even powers. Can you integrate the square of sine or cosine? If you can do that, I'm pretty happy. That's like a good starting point. Past that, it's kind of, a pain. Let's see here. Another example would be something like this. That was example 1, I suppose. So let me see if you guys can do this one now. Example 2. What if I asked you to integrate, say, cosine cubed e to the x times e to the x dx? Could you do this one? So this problem here is a combination of things we've looked at. So like last Wednesday, we looked at how to integrate cosine cubed, right? But there's an extra e to the x here. So what should we do to get the ball rolling, so to speak? Let me suggest this. We'd like for du to be e to the x dx, because if we could do that, then at least all of this would be like just the du, right? If we make du the e to the x dx, what's that make u equal to? You just what? You say e to the x? Yeah. So we should do that. If we do that, then we're just looking at the integral of cosine cubed u du. So now back to a problem that's non-trivial, but we know how to do it. I think we know how to do it. How do we do this problem? I mean, I know how to do it. Do you know how to do it? Simplify cosine into sine, that's a good advice. So we can rewrite this as cosine squared u times cosine u du. So you want to like peel off a cosine because you're going to want to sort of put that into your, substitution. Now cosine squared is 1 minus sine squared u, right? So what should we let's say w equal to what? Well, I think we want this to be the dw. What if we put w equal to sine? I think that would be, like, if we made w equal to the sine of u, I think that would work because then dw, the derivative is cosine. Right, I multiplied the u to the other side, so there we go. Now we've got integral of 1 minus w squared dw. Oh, and that we can do, right? Like the integral of 1 is what? It's w. What's the integral of w squared? Yeah, w to the third over 3, or 1/3 w cubed, right? Plus a constant. Now we just have to go back and unsubstitute, So w was sine of u. I'll go ahead and do it all at once. What's the sine of u, though? U is e to the x, right? So it's sine of e to the x minus 1/3 sine cubed of e to the x plus a constant. There you go. So let me take a poll. Which one do you guys think is harder, example 1 or example 2? Yeah, I think one is harder personally. Yeah, it is. There's just more to arithmetic to keep track of and junk in problem 1. Let's do another example. What if we're faced with the integral of, let's say, cosh of x dx over 1 plus sinh squared x? So let me just remind you guys, what do we know? We know integral of like du over 1 plus u squared. Well, that's inverse tangent of u, right? So that's kind of what pops out in my mind as I look at this problem is, ooh, that maybe is an inverse tangent if I could make the right kind of substitution. And can I? Can I make that kind of substitution? What would I need to make u equal to if that's gonna come together? I would make u equal to sinh, right? So try that. U equals to sinh. If u is sinh, what's du? Yep, cosh, hyperbolic cosine. So with that substitution, we're looking at the integral of du over 1 plus u squared. So it's an inverse tangent. So we get inverse tangent of u plus a constant, but u is sinh, right? So we have inverse tangent of the hyperbolic sine of x plus a constant. There it is.
Okay, there's this spirit that is roaming around. You have, like, you know how to do it when you are in class while you're doing it. But when you go outside there,
When you're outside of class, how do you know how to do it? You have to try something and work it out. Yeah. I mean, I don't disagree. I mean, integration is hard. It's not. You're not wrong.
but we're trying anyway.
Right. Well, I mean, the enemy of progress here is like, everything you don't know about differentiation gets in your way, right? Especially. Let's see here if I can. Let me do another example here, which is a little bit different. What if I had the integral of sine of x cosine of x square root of 3 plus sine of x dx. So you got choices here, right? You could either group you can either group the sine or the cosine with the dx to make your du, right? As a general rule of thumb, if you've got a square root, like probably a good idea if it's just a square root in the numerator, right? The other place a square root comes up where this device wouldn't be valid would be like, if I had integral of like e to the x over the square root of 1 minus e to the 2x, this one I would just look at as integral du over square root of 1 minus u squared, where u is equal to e to the x. And so that would give me inverse sine of e to the x plus a constant. So like there's another problem with square root which looks quite different than this one, all right? But here the square root's in the numerator, so probably, well, I mean, that's kind of it as far as I can think of right off the top of my head. But there's always another. I mean, I'm always forgetting some example. I can never be universal in my advice in here because there's just so many different things you can do with formulas which are within your grasp, which were within your tool set. Now, but here, I think the natural thing to do would be to make u equal to whatever's inside the square root. So that's what I'm going to go with for this one. All right? So if we do that, u equals to 3 plus sine x, that makes du cosine of x dx, right? So we've got cosine of x, we've got dx, right? That's the du. And what else do we have? I'm just going to write it as this is kind of an in-between step. We've got that sine of x that's still there, right? And we've got the square root of u. And dx, well, this and that go together to give me du, right? Okay, well, you're like, there's a sine x left over, right? But can we deal with it? Can we rewrite sine x in terms of u? What is sine of x equal to in terms of u?
Can we substitute using that equation?
Uh-huh. Yeah, like I think that's where I want to go. Let's solve this one right here for sine x. What's sine x equal to? u minus 3, yeah. So sine x is u minus 3. Now we're almost home free, right? Because we're back to something that's just a sum of power functions. Like multiply it out, you've got the integral of u to the 3/2 minus 3 times u to the 1/2 du, which is what? Integral of 3/2 is 2/5 u to the 5/2. And then minus 1/2 plus 1 is 3/2. 1 over 3/2 is 2/3. So that's 2/3 times 3, which is 2. Yeah, minus 2 u to the 3/2 plus a constant. But of course, we have to undo the substitution. So we get 2/5 3 plus sine of x to the 5/2 minus twice 3 plus sine x to the 3/2 plus a constant. I guess that arc sine was example 5. Spend a lot of time on it, but there it is. Let's look at example 6. Suppose you want to integrate 1 plus x cubed, and upstairs you've got, let's say, x squared dx. Can we do this integral?
First of all, the homework I saw there is one question that something like that, but you had what you did in submission there,
Mm-hmm.
where you say x over 1 plus x over x.
Oh, yes. Okay, so, sidebar. If we had integral of 1 plus x cubed over x squared, that is a question I could have asked before. Because that would be the integral of 1 over x squared plus the integral of x cubed over x squared, which would have been integral of x to the minus 2 plus x dx, which would be, like minus 1 over 3x cubed plus 1/2 x squared. Wait a minute. Integral of x to the minus 2 is not 1/3. It's add 1, right? It's just minus 1 over x. So as you can see there, no u-substitution, right? This is just algebra and power rule, basic properties of the indefinite integral. The difference here is the division, the sum is in the denominator. We cannot break this up into like x squared over 1 plus x squared over x cubed. That is just not, it's no allowed. Algebra is not on our side here. So I just got done saying if we have a square root, you don't know what to do with it, maybe try u equals to whatever's inside the square root. That's a good choice. You got a denominator. You don't know what to do with it, right? It's not apparently an inverse sine or an inverse tangent integral. well, then maybe your first order of defense whenever you have a fraction is to try to make u whatever's in the denominator. That's often successful. So here, if I let u equal to 1 plus x cubed, what happens? What's du equal to? 3x squared dx, right? So what are we looking at here? We're looking at, I can solve for dx, feel like dx is du over 3x squared. So what we're looking at here is x squared over, well, u times dx, which is du, over 3x squared. So of course, if the substitution is good, after we make the substitution, we'll just be left with something in terms of u, right? Or like in example 4, something that we can undo and change from x to u without undue difficulty, right? But these guys cancel. And we're left with what? Integral of, yeah, du over 3u. What's that? I can pull the third out, right? So it's 1/3 integral of 1 over u du, if you like. What's the integral of the reciprocal function? Something we need to learn. It is not tangent, no. The derivative of what function is 1 over x? Right, ln. So we put 1/3, and for reasons we talked about, absolute value of u plus a constant. So, because it's actually true that the derivative of the natural log of the absolute value of x is equal to 1 over x. For when x is positive, it's just the same thing again. When x is negative, the details work out to make it still true with the absolute value signs there. Of course, if the absolute value signs are not there and x is negative, well, you have no business. Natural log of a negative number is not defined. So, for this identity to be true for all x not equal to 0, we need to put absolute value. So there it is. And then what do you got? 1/3 natural log of the absolute value of 1 plus x cubed plus a constant. So, yeah. Of course, these problems don't have to be so complicated. I mean, there's like easier version of this one. Example 7. If we have integral of like dx over 3x minus 2. You see something like this, you should just go like, I got to make the denominator the u, right? Again, so I'll make u equal to 3x minus 2. Oops. Good grief. I meant put 1 over here. Dx is du over 3. So 1/3 natural log of the absolute value of u. 1/3 natural log of the absolute value of 3x minus 2. Can happen, not always though, because we've seen that sometimes it's inverse tangent, And notice that it's not, you don't just take natural log of whatever's in the denominator either, generally speaking, like things happen. let's see, here's another similar but different example. If we had integral of like x plus 7 over, 1 plus x squared dx. So I would look at this like this. This is the integral of x over 1 plus x squared plus 7 over 1 plus x squared. And the reason I would do that is because this I know how to integrate. If I tried to make, okay, so like, here's my thought process as a student in your position, all right? If I was in your position, like, my thought process would be like, well, if I make that u, then du is 2x dx, right? But I can't lump in the 7. So that approach is dead. So like, almost, right? It gets the x piece, but it doesn't get the 7 piece. So I need to somehow like split that off. Well, algebra helps me, right? Because if the sum is in the numerator, we have this identity, right? I mean, algebra. A plus b over whatever is a over whatever plus b over whatever. I can break up sums in the numerator. So I did that. And that was good because, can I erase? Okay. That was good because now I have integral of, well, x dx over 1 plus x squared plus 7 inverse tangent of x. Right? Because this piece integrates directly to that. But what about the x dx over 1 plus x squared? Well, now we can make a u equal to 1 plus x squared substitution, right? So du is 2x dx. And x dx, well, what's that? You could write it as 1/2 du if you like, So we have 1/2 du over u. And I've I had to leave myself room for writing 7 tangent, and poor planning on my part. So I need a thought bubble over here. Anyway, but now we're back to your natural log, right? So 1/2 natural log the absolute value of u plus 7 inverse tangent of x plus a constant. But that is the 1/2 natural log absolute value of 1 plus x squared plus 7 times the inverse tangent. Now, this one here, we can do a little bit more to, because sometimes I think about this sort of thing. If I have absolute value of 1 plus x squared, do I need the absolute value signs? Think about it. Is 1 plus x squared negative? Well, no. I mean, 1 plus x squared, if you think about y equals 1 plus x squared, it's a quadratic that starts at y-intercept of 1 and just goes up, right? 1 plus x squared is smallest when it's 1. That's when x equals to 0. So certainly I don't need the absolute value there. And I could bring the half inside and give a square root, right? So you could also write the answer here as the natural log of the square root of 1 plus x squared plus 7 times the inverse tangent of x for what it's worth. Really, either of the last two things are fine answers in my book. So Yeah, I made it into a square root, you know? So natural logs are funny, right? Like, so here's another problem that we can try. What if I had the integral of dx over x squared plus 6x plus 10. So when I was in your place and I saw a problem like this, I would immediately curse there not being an x. Like, I want there to be an x in the numerator, because if there was an x in the numerator, you know, things would be hopeful, right? But there's not an x in the numerator. So what from a sort of intuitive perspective, do you think this should be? What kind of integral should this be? What should it? Do the algebra. Yeah, that's a good idea. So, and by do the algebra, you mean, can we factor the quadratic? Like, what's the nature of the quadratic? And I think I've told you guys before, like, the best way to understand what the quadratic is to complete the square. Right? Completing the square on the quadratic reveals whether what kind of quadratic it is. You know? Like, before we go on with this one, let me do an easier one. Example 10, if we had this, if I had a 9 there instead of a 10, well, then life would be so much easier, because this would be the integral of dx over x plus 3 squared, right? And then in your heart, you would know u equals what? X plus 3. And that's especially nice, because if u is equal to x plus 3, du is straight up dx. And so this is just equal to the integral of du over u squared, which is minus 1 over u, plus a constant, which is minus 1 over x plus 3 plus a constant. So that problem is easier than example 9. And the reason is when we complete the square in example 9 in the denominator, it's not that nice. I mean, it's kind of related. So this completes the square to x plus 3 squared. Now, x plus 3 squared is what? It's this. So we have a 10 instead of a 9, so we still have to add 1. Aha. But now we should make your u-substitution. Make your u equal x plus 3 substitution, because then, well, du is dx. That's one nice thing. And this is just straight up the integral of du over u squared plus 1, which is what? It doesn't matter if it's u squared plus 1 or 1 plus u squared. It's the same, right? They're equal. So yeah, inverse tangent. So that is inverse tangent of x plus 3 plus a constant. There we go.
To me, I could not think about doing how you've done it. I just reach out when
You what?
I'll just reach out when I'll get stuck. Like with breaking down the x squared plus x plus.
Mm-hmm.
I could not add that one.
Oh, well, I mean, if you don't know how to complete the square yet, it's a good idea to go back and practice some more. Like, let's do another one. How about if we have to complete the square, let's say x squared plus 4x plus, oh, I don't know. Eight. So here, to complete the square, you take half of whatever's here, and you add it to x. So half of the coefficient 4 is 2. All right? Now, by doing that, that is giving you back x squared and also 4x plus the 2 squared, right? So technically, to be fair, we have to subtract 2 squared to subtract 4. Now the 8 is still there. So you can always do this. You can always just, if the coefficient of x squared is 1, you can take half of this, do that, and then subtract the square, whatever's there. And then these two terms will collectively be these two. Like, this is a way to do completing the square. But the heart of the matter is you're trying to rewrite the expression so that you're grouping x in a square plus a number. So we don't have to be beholden to the algorithm. We can just think through it. The point is, with this previous one, I've just been, in example 10, I've seen that x squared plus 6x plus 9 is x plus 3 squared. So I look at this, I look at that, I go, well, I've got one extra. So it's just x plus 3 squared plus 1. But if I went through this song and dance, I would have had x plus 3 squared minus 9 plus 10, which would have been this also the same. So like this one here, though, what do we get? We get x plus 2 squared plus 4, right? So how would this, let's call this example 11. How would we face the music here? Integral of dx over x squared plus 4x plus 8. Right? We can complete the square like we just did above. And what's the trouble? Plus 4. But we don't know how to deal with plus 4. What do we know how to deal with? 1. How can we convert that 4 into a 1 and so make this a problem that we can do? How do we change that 4 into a 1, essentially? One over 4 dx. You want to factor the 4 out? I mean, oh yeah, that's plus. Yeah, we can't just. But you're actually not far off track. I mean, that's the idea. We want to factor 4 out, but we have to factor it out of the denominator, right? Now, so I have to put x plus 2 squared divided by 4. And factoring 4 out of 4 just gives me a 1. to factor 4 out. 4 times 1 is 4 again, right? 4 times this is x plus 2 squared again, so. But I agree, this is like a, did you ever do this in algebra class? No, because it would have been a crazy thing to do, right? I mean, but here it's not. It's just the right kind of craziness here. So this is 1/4 integral, and I'm going to write this dx over 1 plus, and let me rewrite that suspiciously as x plus 2 over 2 quantity squared. So then what? See, now I think I've manipulated it enough that you can hopefully see we're tending towards an arctangent integral again, right? So we can let u equal to this right here. So then du is dx over 2, right? And so what we're having here is 1/4 integral, so dx is 2 du, right? So we have 1/4 2 du 1 plus u squared. So the 2 and the 4 give me a 1/2. Inverse tangent of u plus a constant. And so there you go. 1/2 inverse tangent of x plus 2 over 2 plus a constant. So if you kind of take a step back and think about what we've done, we've now seen how to integrate 1 over a quadratic in the case that the quadratic is what? It's a repeated, like if it's a square, just a pure square like this, a repeated root, or if it happens to have complex, a pair of conjugate roots, if it's an irreducible quadratic. We can complete the square and we can make this kind of sneaky little pull the number out trick, and it's going to give us an inverse tangent of whatever this completed square term was divided by a particular number. Now there's one other kind of quadratic, right? What if I had the integral of like dx over, I don't know, here's one, x minus 2 times x minus 3. What would you do there? I mean, we could go back to completing the square again. You know, maybe that would be a successful endeavor. Did we talk about I think we could use like inverse hyperbolic tangent to do it that way. I'm trying to remember. Do you guys happen to know off the top of your head what was the derivative of the inverse hyperbolic tangent? I'm sensing that's a no. I can work it back out. It'll take me a minute. Should I work it back out? It might be a good review for the final, right? Because one of the things that we'll have to do on the final is derive, derivatives of inverse functions. So here I'll go through it. I don't want to erase that. I don't want to erase that. I don't want to erase anything here. I can do it over here. So we start out with y equals to inverse hyperbolic tangent of x. We take the inverse hyperbolic tangent of both sides. Or rather, we take the tangent of both sides. tangent of y is equal to x, right? Then we differentiate it. What do we get? What's the derivative of tangent? The derivative of tangent is hyperbolic secant squared. But chain rule gives me dy dx equals to 1. Remember that cosh squared y minus sinh squared y is 1. Dividing by cosh squared gives me 1 minus tangent squared is hyperbolic secant squared. So this gives me dy dx is 1 over hyperbolic secant squared y, but that is 1 over 1 minus tangent squared, which is 1 over 1 minus x squared. So there we go. The integral of dx over 1 minus x squared is equal to the inverse hyperbolic tangent of x. And for our purposes, it's useful to multiply this by minus 1, just to make it more natural. The integral of dx over x squared minus 1 is minus the inverse hyperbolic tangent of x plus a constant. So if I want to go down this path, this would allow us to do integrals of the other kind if we wanted to. Let's see here. Let's see here. So what I'm really faced with from this viewpoint is dx over x squared. Oh, how horrible. Minus 5x plus 6. So if I complete the square on that, I get x minus, oh, fractions. I hate fractions. X minus 5 halves squared. So that means I have to subtract 25 over 4, right? And I still got the 6. How many 24ths is, how many fourths is 6? It is 24 sixths. Oh, good grief, 24 fourths. Words. Oh. Now that's actually kind of nice because you end up with a half there. I mean, you end up with a quarter, which is just half squared. Now, given the derivative I just worked out, we know how to deal, we know how to do the integral of du over u squared minus 1. We know that that's minus the inverse hyperbolic tangent of u plus a constant, right? So the trouble here, of course, is I got this annoying fourth. So I do the same trick I did in the last example, which is I factor the fourth out. And so, how's that look? One quarter, right? Of, well, this one gives me 4 times x minus 5 halves squared, right? Minus 1. So I'll bring the, what's 1 over 1/4? That's just 4, right?